Thank you, Eric. Thank you, Alex, for your kind invitation. So it's a great pleasure to give a online Zoom talk at this famous UQ hybrid seminar. So, today, I will talk about some recent work on this deep particle method. As Eric mentioned, before I worked some UQ problem, and when Eric sent me an invitation, he asked me which topic. I sent him two topics, and he told me this one be more popular, so I choose this one. So this I will talk about this uh, so deep particle method to learn and generate distributions for many problems. So this is joint work with two of my former students, Dr. Li Junlong and Dr. Wang Zhongjie. Professor Wang is right now at work at NTU Singapore, and also with Professor Jack Xin from UC Irvine. So my plan is the following. So first part is give you some motivation. Why do we develop this deep particle method? So this is a previous research. And the second part is the main part. I will briefly discuss this deep particle method, such as how to derive this method and how to train the network, etc. And the third part is some numerical method. I will tell you how to basically two applications. First one is use this deep particle method to learn and generate invariant measure in computing KPP from speed. And the second one is to learn and generate these aggregation patterns in Keller-Segel chemotaxis system. And finally, some conclusion. All right, so I will try to briefly, because the first part is some motivation, physical motivation. I will quickly, I will skip some time for this convergence analysis part. So, okay, let's start. So first is this motivation. Before we started this so-called KPP from the propagation in this reaction diffusion advection equation with the KPP nonlinear term. Basically, we studied this problem. So imagine you have some kind of such as a turbulent combustion or this industrial deposition process. You want to study how this front propagate. What is the front speed modeled by this PDE? Well, this is a nonlinear PDE, so people will linearize it, and there's some linearized version. So so before this KPP from speed problem was well studied, if the velocity field is well structured, such as regular motion, for example, periodic, or fully random. However, when the velocity field here V is chaotic, so there was a less studied before. So a typical example include this ABC flow and Kolmogorov flow. So we studied this case, okay? So as I said before, the nonlinear PD is not easy to study, so people linearize it and study this eigenvalue problem. So linearize the PD and you solve this equation two, and compute the principal eigenvalue, and divided by lambda and compute the inf. And if you compute this quantity, this will give you the minimal front speed in direction E. Here E is any direction. Okay, so you compute this. Essentially, that means if you want to quantify the front speed, you need to compute the eigenvalue problem like this, right? Then you can tell us. You can get what is the minimal front speed in any direction E. Okay, so before some scholars they use some adaptive finite element method to compute this principal eigenvalue for two-dimensional and three-dimensional problem. Okay, and here the V is does not depend on t. Okay. Similarly, if your width depends on t, you can repeat the same procedure, and again you solve this principal eigenvalue. However, right now you need to solve a parabolic type. Parabolic type. So before, people also apply so-called edge average FEM with the algebraic multigrade method to compute the principal eigenvalue for this problem, but only for 2D. Only for 2D. Okay. So in both cases, to compute the eigenvalue problem in 3D is expensive. Also, if the diffusion parameter kappa is small, compute the principal eigenvalue is also expensive because you have this advection dominant problem. Okay, so the question is, can you propose other method to compute this principal eigenvalue? The answer is yes. So before we use this, we in our previous research we developed the structure preserving scheme to compute the this effective diffusivity in 2D and 3D, chaotic flow, stochastic flow, etc. So this motivate us to develop particle-based method to compute the principal eigenvalue. Okay, so here is the idea. So for example, if you consider a linearized equation with this ut equal this operator, and this principal eigenvalue is essentially is a Lyapunov exponent of this parabolic operator. Okay, so that means you can design so-called Feynman-Kac formula to compute this principal eigenvalue. Okay, so the idea is very simple. We split this operator into L and C. Here, L is the diffusion advection operator, and C is the potential operator. Okay, and from the operator L, we can construct SDE system as the following 6. Okay, then plug in the formula for C, you get this by Feynman-Kac's formula, the principal eigenvalue mu has a formulation in this form. Okay, so that means this is a very elegant formula. This provides us an alternative approach to compute principal eigenvalue. Okay, so I mean you simulate this SDE and plug in this equation and take a limit, and you can get the principal eigenvalue. Okay, so mathematically this equation 7 is very beautiful, very elegant. However, numerically this is not very good. Why? Because when you do simulation, you simulate some trajectory and plug in this formula. You need to compute the exponent and you need to compute the log. This is a highly nonlinear, so this will bring instability in simulation. Okay, for example, some value, if you take exponential, become very large or very small. So this will introduce many numerical issues. Okay, so how to overcome this? So here is message is directly use the Monte Carlo method to compute the principal eigenvalue while the Feynman-Kac formula is unstable. Okay, so here is a very powerful idea. So remember in numerical linear algebra, we all know learned this so-called power method or power iteration method to compute the value of a matrix. Okay, so essentially we do I mean for matrix A, you randomly generate a vector, you multiply A to this vector and normalize, multiply again and normalize. So I mean every time you need to normalize. This normalize will avoid this blow up. Okay, so the power method works for finite dimensional space, vector space, and here in the mathematics book there is a so-called Feynman-Kac semigroup that works for measure. So I mean similarly we can you can view this as a power method in infinite dimensional space or measure space. Okay, so in the textbook, there's a very beautiful series, so-called the Feynman-Kac semigroup. Okay, so essentially we need to define this two operator. One is a P, another one is a PC. So for any measure nu, any test function phi, we just evolve this measure by our SDE, and this PC is a weighted part, right? So you can easily verify the infinitesimal generator for P and PC are L and A. Okay, so equation 10 is a key idea. So you can view this as similar to the power method. So the Feynman-Kac operator is defined as the following: for any measure, for any time interval t1 to t2, you in the numerator you evolve this measure, and in the denominator you normalize it. Okay, so that's the definition for the Feynman-Kac semigroup. We can verify this definition satisfies the semigroup property. Okay, in our simulation, we don't choose an arbitrary time interval. We fix time t, so we can define this Feynman-Kac semigroup in the following. Okay, for this capital T is a fixed time period. Okay, and for the steady flow, we can arbitrarily choose a t equal 1. Okay, so we can define this. All right, that's a beautiful theorem is this one. So if your operator A, your eigenvalue has a spectral gap, delta C, that means the first eigenvalue and the remaining part, the real part, you have this gap, delta C. If your operator satisfies this property, and you can you get this, your semigroup for any measure nu, you do this iteration using Feynman-Kac semigroup. It will converge to the inverted measure nu C exponentially fast. Okay, and this decay speed depends on the spectral gap. So when your iteration converges to the inverted measure, you can compute the principal eigenvalue by some integration. Okay, so this beautiful theorem provides a very alternative approach to compute principal eigenvalue. It's just like in the power method. Remember, in the power method, we can use this iteration normalize. It will converge to the first eigenvalue if your first eigenvalue and the second eigenvalue are not equal. Okay, so yeah, that's the idea. Okay, then I quickly show you these details. Remember, in our method, we need to solve SDE, right? We solve SDE, and remember the capital T is a period. So the idea is for each period capital T, we divide it into m intervals. Delta T is a time step. So within this small step, we solve this SDE, and we can. By the way, sorry, I need to mention this. In equation 10, it's very beautiful. However, it's just a mathematical analysis. This is new and it's a measure. In real computation, we cannot, use use a pen to analyze this. We need to do numerical computation. So we have to approximate this measure by particles, empirical distributions. Okay, so that means we approximate this this measure nu by n particles. Okay, we need to do sampling, right? So you sample n particles from this distribution summation or delta function, and use that empirical distribution to approximate this inverted measure. Then you do evolution for these particles, n particle system. Okay, so that's a numerical approximation. So yeah, we have to define the discretized version for the Feynman-Kac semigroup, and we approximate any initial measure by this n-particle system. Then the evolution from one period to another is we need to solve SD. Okay, yeah, here this slides show you the details. So at any step, imagine you at this time you have n particles, right? N particles, Kc1, Kc2 to Kcn, right? Then first you use one step Ola Maruyama to solve the SDE. You get this. Then you do a resampling. According to this multi-normal distribution with this weight. Remember, in this resampling part, we will take into account the C, okay? And do solve resampling, then solve the SD continue one time step, and resampling, one time step, resampling. When you finish one period, then repeat, okay? So let me say again. So within each period, n-1t to nt, you solve this. One step resampling, one step resampling. When you finish one period, then repeat. Okay, so this in this code you have a two loop, right? Outside loop, you loop over n. Then within the loop, you solve this SD for one period, 0 to t, 0 to capital T, right? Do this ODE, solve SD and resampling, solve SD and resampling. Okay, so this is the whole algorithm, And when you compute, you can record all this intermediate result, and you get this equation 25. Okay, this will give you a numerical approximation to the principal eigenvalue. Okay, so this is algorithm. Okay, I skip this analysis part. Okay, we after do some derivation. The idea is very simple. We study this solution operator, and we use the operator splitting method to approximate this solution operator, and we do some analysis, use some analytical semigroup property, and we can prove this theorem here. So this one is a numerical result, and the right-hand side, lambda nu is a exact eigenvalue. So their error is have two parts. One is a time step, time discretization. Another one is iteration, the Feynman-Kac semigroup iteration. So, this analysis is not very sharp. Okay, so I mean, this analysis only give an upper bound for the error. In our computation, we can find a better performance than this. But anyway, this theorem give a convergence result for our method. We call this interacting particle method. Okay, so yeah, let me start some numerical part. Okay, so after we obtained this interacting particle method, so-called IPM, we compute several applications. For example, we compute the KPP from speed in different flows, such as a 2D static flow and 3D ABC flow. So here is a static flow. Okay, there's no time dependent. That means we need to solve this elliptic operator. 2D with this and 3D with this. Okay. The good news here is remember if you solve eigenvalue problem use a finite element or spectral method, your complexity increase exponentially fast with respect to D, right? However, if you use this particle method, remember in the particle method, we just solve SD. So the complexity is linearly depends on D. Okay, not exponentially depends on D. It's linearly depends on D. Okay, so for 2D, you solve SDE for two components, and for 3D, you solve SDE for three components. Okay, both are very cheap. All right, so here is some convergence performance. The convergence rate with respect to time is bigger than half. Okay, so that means our analysis is not sharp. Uh, all right. Then we, okay, for this 2D unsteady flow. So that means right now the flow depends on T. Okay, so if you compute the principal eigenvalue, you need to solve a parabolic type operator. Okay, uh, so if you solve this eigenvalue problem, use the finite element or spectral method. This T will increase. It will add another degree freedom, right? Another dimension. So you have a 2 dimension in physical variable and 1 dimension in time. So that's also expensive. However, if you use the particle method, it's still the same, right? You just solve SDE and your drift term depends on T. That's okay, right? So that means the complexity is still very cheap. Complexity for the IPM is very cheap. Okay, so that's another advantage of this particle method. All right, so next, in the physical, this paper, people are interested in how this front speed depends on the, strength of the flow, A. Okay, some physics like some power law, how this front speed depends on the strength of the velocity. Okay, and we can, well, in the literature, people can derive a beautiful theorem like if your flow is a 2D cellular flow, uh, the this front speed is proportional to a to the power 1/4. Okay, so that's this power, and the people can also for this cellular flow, people can prove that their effective diffusivity is proportional to a to the power 1/2. So that means for this simple 2D steady flow, cellular flow, the front speed and the effective diffusivity satisfy this relationship. Okay. And because in our previous work, we already have a structure preserving scheme to compute this effective diffusivity, so we can numerically verify this relationship is true. Okay, in this 2D cellular flow. And we can also do some conjecture, and we see this for 3D K flow. This relationship is also true. However, we don't know how to prove because for 3D, very complicated. The streamline is very complicated. Okay. Next is we studied the evolution of this empirical distribution. Remember, in our method, right? Remember, it's based on Feynman-Kac semi-group. You need to do this iteration many, many times, right? So, for example, here, in your problem, your effective diffusivity, sorry, your diffusion parameter sigma is a parameter, right? If you decrease the sigma, you can see the inverted measure will develop some structure like this sharp gradient or concentrated region. Okay, so it's a very beautiful, right? For the time-dependent case, we find that inverted measure has some periodical structure. Okay, so here is a question. Look at this picture. Look at this picture. That's another example, but also the effect, the diffusion parameter sigma is a constant, is a parameter. Okay, so look, if you here this one is sigma equal to the power 0, to the power -1, to the power -2. 2 to the power minus 3, 2 to the power minus 4, and 2 to the power minus 5. See, if you decrease your sigma, your inverter measure will develop some sharp gradient, right? So I mean, when you compute the eigenvalue, right? So for each case, you need to start from initial distribution. For example, if you start from a uniform distribution, right? Because this inverter measure is relatively smooth, so you may need like a 500 or 1000 iteration, you get a convergence, right? However, for this one, it's a very, you have this sharp gradient, okay? So if you start from uniform distribution, you may need like a 10,000 or more than 10,000 iterations to converge, right? So that means if your problem become harder and harder, you may need more iterations to converge, okay? The reason is your initial distribution is not good, okay? So here's the question. Can you learn how this distribution depends on sigma? How this inverter measure depends on sigma? If you can learn this, okay, if you can learn this, use a machine learning power tool or deep learning tool, then, I mean, if you learn this, you can learn this, that will be good. Because if you input another, so if you can learn this relationship, so if you want to compute even smaller sigma, you just input that value, say 2 to the power minus 6 into the deep learning model, and that will give you a result, okay? And you can use that as your initial distribution to do iteration. It will converge faster than start from a uniform distribution. Is that clear? So yeah, is this clear? That's the key point for our method.
Yes, I think so.
Okay, I have pause here if
Maybe,
you have questions.
do we have any questions otherwise?
I have a
Okay,
few questions,
yeah.
but okay. Is it okay if I ask them now or
If you're related to this, you can ask. Otherwise, you can ask after the talk.
okay, then I'll ask them later.
Okay.
Thanks.
Thanks. Okay, so here, this picture, I give you the motivation. Why do we want to develop this DeepParticle method? Why do we need to learn this relationship? Because if we can do so, we can, have a very cheap method to generate initial distribution. Okay, so that's our motivation. So let me start the second part. Okay. So the second part is we want to develop this DeepParticle method to learn and generate distributions. Okay. So to learn, so machine learning in the deep learning we need loss function, right? So in our setup, we are dealing with measures, right? So it's very natural idea is using this Wasserstein distance to measure the difference between measures, right? So here's the definition. Uh, so yeah, let me say again. The key idea of our method is we want to learn how this measure depends on sigma. Okay. The good news is if sigma is not very small, we already get several data set, right? We already get this data set. So we can use this data set as the training data set to learn this relationship. Okay. So so essentially we want to learn this push forward map from one measure to another. Okay. Uh, yeah, again, because we are dealing with a numerical method, we have to approximate this measure by empirical distribution, like this summation of n delta function. Okay, this trick. And in this setup, this joint distribution will be approximated by this doubly stochastic matrix gamma. Okay, with a constraint that for each index, summation row and summation column are equal to 1. Okay, because they are marginal diffusion. All right. So we let me see. Okay, here is the idea. Very simple. I mean, this idea very simple because remember, guys, we already get many data set, right? So we want to train this neural network uh, uh, by minimize this loss. Okay, so outside there is a summation eta n eta means how many data set do we have, and within this, for each we have this input and output. One measure to another, we want to map this measure to another, right? So we can use this as a loss function. We can use this as a loss function, and sum them together. We have this training loss function for our method. Okay, I skip these details. The training. Okay, guys, the training is this. So first remember, forget about this. For each of this, right? In the training, we need to deal with the two part. One is we fix the neural network parameter eta, and we will adjust this weights gamma by solving this linearization problem or OT problem. And then fix gamma. We use SGD to update the weights in the neural network. Then fix this and update the gamma, and fix gamma and update theta. So this is a alternating procedure. Okay, there is another thing I want to tell you is here, fix theta. We essentially solve this optimization transport problem, optimal transport problem, right? Then if this n is very large, solving this OT problem is very expensive, very expensive. So inspired by this mini batch method and this domain decomposition, we propose a very simple idea. We call this random block coordinate descent method. That means it's like a mini batch method, right? We don't use all the n together. We randomly select m row and m column, and we solve this subproblem. And do iteration. Okay, and later on we prove this strategy is convergent, and we also have some speed up. All right, this is our network. In our network, we have two inputs. One is a physical variable x, that's a position for the particles, and we also have a input for the parameter eta. We call it the parnet. So we have this parnet structure. Later on, we also investigate other structures such as CAN or other structure. We are still working on it. But in our first paper, we just use this very simple parnet. And let me show you some example. First one is a mapping from uniform distribution to normal distribution. This is the example. Second one is this one. This is more beautiful. It's learn this invert measure for the KPP problem. The lower row is a reference, and the first row is generated by our DeepParticle method. Okay, it's very nice. So after this training, here, look at this picture, very, very beautiful. So this one, okay, this is some prediction. Okay, so left is so remember guys, we solve this invert measure, right? For sigma equal even small sigma, this one is a ground true. Okay, you know, for example, you start from uniform distribution, you may need like 10,000 iteration, and you get this invert measure. And this one is a prediction by our neural network. Okay, prediction by neural network. So although it's not very similar, not the same, if you use this one as the initial training data, if you use this one as the initial distribution, you can quickly convert to this one. Okay, so this you can view this as a preconditioner for the IPM. I hope I use this figure to explain our idea. Later on, we also investigate other applications. Here is one. Many physical problems, their physical meaning is a distribution. For instance, the famous Keller-Segel chemotaxis system. You have this two PD system. Rho is the density of the bacteria. Rho is the density of bacteria, and C is the density for the chemotaxis. Okay, and especially people will do some simplification, and they study this parabolic elliptic case. That means epsilon equals 0, and you solve this PD, solve C by Green function, plug in, you get this one. You get this one. And people will add external velocity to model some external environment. So this is 49. 49 is so-called McCann-Vlasov equation, and it has a SD representation here. Okay, so that means you can solve this SD system, and these particles will convert to the rho in distribution sense. Okay, so this provide another example to test our DeepParticle method. So we do the following. Okay, so let me show you this one. We do this. So from time t equals 0 to time t equals 0.1, well, our time step is a 0.01. So totally we have 11 data set, the training set. Okay, with this training set, we train the neural network and to learn how this distribution or solution depends on time t. Okay, so in this example, time t is a parameter. We want to learn how this solution depends on t. Okay, there's a beautiful theory show that if your critical mass is bigger than the initial mass is bigger than critical mass, and for this Keller-Segel system, the solution will blow up in finite time. So in this setup, the theoretical blow up time is 0.125, and here is our result. So remember, t equals 0.1 is the largest time in the training data. Okay, so this one, t equals 0.12 is the extrapolation. Okay, extrapolation. But still it's good, right? Network output is our DeepParticle method, and reference is a reference solution obtained by the interacting particle method. Okay, this is one example. You can see the distribution is very sharp, like it will gradually develop into a delta function. However, in this case, our DeepParticle method is also still good. Another example, in this example, we choose the strength of the velocity as a parameter. A is the strength of the velocity. Okay, so imagine you have some bacteria here. You input a flow in the x direction. Okay, see, there are some theories show that if you add this external velocity field, it will postpone or avoid blow up. Okay, so you can see as A become bigger and bigger, your density become curved like a cat, right? Like cat. So in this setup, the biggest A in the training data set is 100, and this 150 is another extrapolation. Okay, so that means this deep particle method can kind of depends on the quality of your training data, can learn this aggregation pattern in the Keller-Segel chemotaxis system. Okay. Later on, we also study some 3D case. 3D is also fine. This 3D and this projection for any two dimension. Okay. And again, this 100 is the biggest one, and 130 is the extrapolation. Yeah, I also show you that we also prove the convergence for the mini batch method, and we have the accelerated version. This one has a similar performance to the single algorithm in solve the OT problem. Yeah, so I think that's the talk I want to discuss. So here's the conclusion. So in this talk, we develop an interacting particle method to compute the principal eigenvalue of advection-diffusion operator. So we can compute the front speed in RAD equation with the KPP nonlinear term. So the key idea for this method is to evolve the empirical distribution of particle to inverted measure, and from this we can compute the principal eigenvalue. Then from the principal eigenvalue, we can estimate the front speed. So this method is mesh-free and self-adaptive and very cheap. Okay, compare with the finite element or compare with the spectral method, it's very cheap. However, remember in this method, we need to evolve any distributions from initial distribution to inverted measure. So if your inverted measure has some sharp gradient, to this evolve iteration is very expensive. So this motivates us to learn how this inverted measure depends on parameter. So we develop this DeepParticle method. So this DeepParticle method can learn a family of inverted measures by using neural network. So that's the first example. Secondly, we also use this DeepParticle method to learn and generate aggregation patterns in Keller-Segel chemotaxis system. So that's the second application. Right now, we are working on other version of this DeepParticle method. For instance, we want to compare the performance of this DeepParticle method and the diffusion model in this PDE problem. Okay, so that's the okay. Thanks support from the NSFC and the Hong Kong RGC, and thank you very much for your attention.